Let's now consider this problem involving confidence intervals, both two-sided and one-sided, and also a prediction interval. We have 18 independent measurements of the melting point of tungsten. The sample mean is 3,410.14 degrees Celsius, with a sample standard deviation of 1.018 degrees Celsius. The question is to find a 99.9% two-sided confidence interval for the melting point, and then to secondly find a 99.9% confidence interval that gives a lower bound. To do this problem, we first realize that we need to use a t-distribution because we have a small sample size. For the first problem, we have a 99.9% that's two-sided, and so the picture is going to look like this. We want 99.9% to lie in the middle. And therefore, the area in both tails would be 0.0005, so that the area over on this side also is 0.0005. And then we find the appropriate t-value, and in this case there would be the t-value of 0.0005, corresponding to a t-distribution with 17 degrees of freedom, using n-1 for the number of degrees of freedom. Okay, now there are two ways of doing this. If you have a TI-84 plus or higher, or else you're using Microsoft Excel, then we can find this using tinv, inv-t off the TI calculator, and it's t.inv off of Microsoft Excel. For illustration purposes, I'd like to do this one using the table. So 17 degrees of freedom, and I want the area to the right to be 0.0005. So here's the table that's in the back of the book, and we see that on the very last row here, hopefully on the screen, that 0.0005 is the value to the right, so that's the number on the top row. And the number of degrees of freedom is going to be the value new here in V, or looks like a V. And so 17, we have 3.965 as the critical value. So we'll write that down, that the critical value here is equal to 3.965. If you're using the technology, you probably get the more accurate answer of 3.9651262. But this is certainly good enough for the calculation that we're about to do. And so the two-sided confidence interval is going to be 3,410.14 plus or minus 3.965 times the sample standard deviation of 1.018 divided by the square root of 18. And so this works out to be 3,410.14, and then just doing the arithmetic, plus or minus 0.95 degrees Celsius. So that is the answer to problem number 1. For problem number 2, we'll do that on the right side. This time we want a one-sided confidence interval that also remains at 99.9% confidence. So perhaps the issue is to determine the worst case scenario, how small could the melting point be. So in this case, the picture is that I want the area to the left to be equal to 0.999. It's a one-sided confidence interval, so the area in the tail will now be 0.001. And so the t-value that I want this time will be t sub 0.001, and once again with 17 degrees of freedom. Okay, so this time, looking on the table, 17 degrees of freedom, but this time I want the area to the right to be equal to 0.001, and so the critical value will be 3.646. So this number is a little bit smaller than the number that I had before. Before I had 3.965, this time I have 3.646. Makes sense because I have more area to the right, and so this number ought to be smaller than this number, which has less area to the right. Okay, so the lower bound will be that mu is going to be bigger than 3,410.14 minus 3.646 times 1.018 divided by the square root of 18. And doing the work, we get that mu is greater than 3,409.27. Okay, so we have two pictures here. Let me kind of draw them out here. So here's 3,410.14. And in red, we had this prediction interval. The small portion would go down to 3,409.19. And on this side, it would be the same amount on the other side, and going up 0.95 to 3,411.09. And so the first calculation says that I am 95% confident that the true value of mu lies in this range between the red hash marks someplace. The second calculation, 3,409.27, would be right here about, say, approximately. And the second calculation says I am 99.9% confident that the true value of mu lies to the right of that green mark someplace. So using the two-sided or the one-sided confidence interval depends on which one to use, depends on the importance of either measuring the value accurately or else stating the worst-case scenario. Okay, let's now turn to the third part of this problem. So clear off the screen here a bit. Under the assumptions of normality, find a 99.9% prediction interval for the next measurement. So this is a question that's not concerned about getting the an accurate measurement of the population mean. It's just if I do it the next time, what do I expect that value to go in between? So the formula for this time goes like this. We have x bar, 3,410.14, and we have its default assumption is that if I say prediction interval and I don't say it's two-sided, then it's two-sided. I would tell you a one-sided if the if I wanted that. So plus or minus. Because it's two-sided, I'll use the exact same number that I had before, 3.965. And the formula goes this time times the value of s, 1.018. But instead of dividing by the square root of n, I multiply by 1 plus 1 over n. So the thing that's new is the 1 plus. If I erase this, if I just simply erase this, then the formula that you see on the screen is exactly what I had before in red for the 99.9% confidence interval. However, by adding the 1 plus in here, I have now changed this so that I'm not getting the confidence interval now, but I am getting the prediction interval. And so doing the arithmetic, we get 3,410.14 plus or minus 4.15 degrees Celsius. So I am 99.9% confident that when I measure the melting point the next time, it's going to be in this range someplace.